So today's poser. Which requires more work? Increasing the speed of an object from 0 meters per second to 1 meter per second? Or from 1 meter per second to 2 meters per second? The choices are from 0 to 1, from 1 to 2. Both require the same amount of work, or it can't be determined. I encourage you to sit, pause the movie for a second, and think about your gut feeling for this answer, and also how you would solve it if it were extremely important that you get the right answer. In other words, how you do it if $1 million depended on whether you get the right answer. So please pause the movie and think it over, and then return once you've thought it through. Okay, so hopefully you've come up with the correct answer. It takes more energy to go from 1 meter per second to 2 meters per second than it does from 0 to 1. And the reason for this, if you go back to the square term in the kinetic energy expression, you can see that since the energy is dependent on the square of the speed, the faster you go, the harder it is to accelerate. Okay, if you didn't get that, please go ahead and review that, because it's a very important concept and one that's often challenging for budding young physicists. Hello, I'm Mr. McBrien. This is SPH3U, Conservation of Mechanical Energy, or my fun term for it, the Forever Ball. Okay, the Ontario curriculum states that students will use the law of conservation of energy to solve problems, and that students will be able to describe a variety of energy transfers and transformation and explain them using the law of conservation of energy. Today, we're going to talk about the law of conservation of energy, apply that law to some problems we previously might have solved in our kinematics unit. Okay, what I'd like us to start with now is the consideration of the problem of a ball suspended in air. So I've put a cartoon together showing, first let's focus on state 1. So a ball suspended 12 meters above the ground, and it's held so of course the velocity is 0 meters per second. So that 3 kilogram ball is suspended at a height of 12 meters above the ground, and we want to calculate its gravitational potential energy. So we can do our familiar process. Remember that energy equals mass times g times h. We can substitute in, and it's a pretty trivial exercise, to find out that we get a number of 350 joules. The gravitational potential energy of our object is 350 joules. So what about the kinetic energy? Well, we have an expression for this now. Our velocity, because it's suspended in the air, is 0 meters per second. E equals 1/2 mv squared. And the energy equals 0. No great surprise. It's not moving. The kinetic energy is 0. So this is our basic situation then. Our velocity, 0. Our gravitational potential, 350 joules. And our kinetic energy, 0 joules. Now we release the object, and we let it fall towards the ground. Now let's calculate the speed of the object when it hits the ground using our kinematics equations. So v1 equals 0 meters per second, the acceleration is negative 9.8 meters per second squared, and our distance is negative 12 meters from our original position. we can rearrange our standard equation to get V2 equals 2 times negative 9 meters per second squared times minus 12 meters. And again, fairly simple algebra, and we wind up with our velocity equals 15 meters per second. So that's our situation down here. Our velocity is 15 meters per second. And if we take this state as being, or this point as being zero height, of course our gravitational potential energy is now zero. But we can calculate our kinetic energy too. So we have an expression for this. We'll add that sig fig back on that decimal place as we do this calculation. We can get our kinetic energy, and lo and behold, 350 joules. So back to our little diagram then, and we have a fairly complete diagram. Gravitational potential energy of 0, kinetic energy of 3.5 times 10 to the 2 joules. And notice what's happened here. We've gone from 0 kinetic energy to 350 joules, and gone from 350 gravitational potential energy to 0 joules. In other words, all of our energy has gone from gravitational energy, potential energy, to kinetic energy. And if this ball were to bounce and head back up in a perfectly lossless bounce with no air friction, we'd expect the ball to go back up to the same height again and return to the situation of 100% gravitational potential energy, in other words 350 joules, and 0 kinetic energy just as it stops. So the energy is moving between potential energy and kinetic energy as the ball bounces. Okay, so as we said, we've got a transformation from gravitational potential energy to kinetic energy. And of course, if we were watching closely, the total energy, 350 joules, didn't change. And in fact, if we had chosen any other spot on our falling, any other spot in our fall, we could have done different math and still gotten the same result, that the sum of the potential energy and the kinetic energy doesn't change. And this leads us to a general expression for this idea. So the law of conservation of mechanical energy states that in general, if no work is being done on an object by an outside force, the total mechanical energy of the system remains constant. And we could write this as delta E equals 0 for a closed system. Or we can get a little more explicit and talk about the sum of the gravitational energy plus the kinetic energy. So the gravitational potential energy plus the kinetic energy, the sum of this at a given time point must equal the sum of the gravitational potential energy plus the kinetic energy at a different time point, provided no work is being done on the object by an outside force. In other words, provided we have a closed system. So let's take another example. We launch an object from the ground with a velocity of 12 meters per second up, and we want to find the maximum height of the object. Now remember, at maximum height, the velocity equals 0. And that's all we need in order to solve this problem, is to know that at maximum height, the object stops going up. So we have a v1 of 12 meters per second, the initial height of 0 meters, and a final velocity of 0 meters per second. From that, we need to find the maximum height, or h2. Well, we can use our expression for conservation of mechanical energy, and substitute in. Now what's interesting here is we have two easy calculations, right? Because initially our height is 0 and the gravitational potential energy is 0. And at our final situation, the kinetic energy is 0 because we're not moving. And then we're left with this expression here, 1/2 mv1 squared equals mgh squared. Equals mgh2. So we find something interesting here, right? We don't have a mass. So how do we solve for this? Well, we have to recognize that the mass term is contained in both expressions, and so we can divide by mass without changing the truth of this equation at all. And after we do that, we get 1/2 v1 squared equals gh2. And of course we're solving for h2, so we need to isolate for it. So we divide both sides by g, and h2 equals 1/2 v1 squared over g. And we can move the 2 down to the bottom, of course, and we get h2 equals v1 squared over 2g. And substituting in, the height that we will reach is 7.3 meters. And if you wish, you can use your kinematic equations to solve that problem in that manner, and you will get the same result. Okay, one thing worth noting is that I described the idea of a ball bouncing back up to the same height it started at. And I described the concept of the kinetic energy being identical when just before the ball hits the ground when we drop it. The kinetic energy being the same as the gravitational potential energy was when just before we dropped it. In real life, the energy is never transformed with 100% efficiency. A ball dropped from a given height won't bounce back up to that same height. No matter how good a super ball you have, it won't manage it. We have air friction, we have losses due to noise. There's lots of reasons why it won't be 100% efficient. So all we can do is approach 100% efficiency for these kinds of things. We'll neglect these losses for most situations. So, those are the basic concepts around the law of conservation of energy. Please do go and read your textbook and then attempt the practice problems listed here. Thank you and have a great night.